So I don't have any big questions left. Are there any smaller questions you'd like to address?
All right, Peter, since you phrased it so eloquently, some students have wondered or they've heard acronyms like LL, LR, or LALR bandied about, perhaps on the forums or mentioned by other students who have taken similar topics, and you might wonder, what do those mean? Those acronyms are all subsets of context-free languages or context-free grammars. They're grammars that are written in a special way to make them easy to parse. The parsing approach that I've taught you in this class, where we build up the chart of parsing states and memorize things, can handle any of them. It handles LL, it handles LR, handles LALR, and in fact it handles context-free grammars. I think a lot of those previous approaches, LALR in particular, are really historical accidents. They were restricted classes of grammars that engineers made back in a time when computers were significantly slower, and we had to squeeze every drop of blood from the turnip that we could. We had to squeeze every ounce of performance that we could out of the hardware available. So we said, oh, it's better if I, a human, spend a lot of time refactoring my grammar to make it easy for the parsing algorithm. These days, I think your time, the human's time, is more important than the computer's. I want to be able to write down the grammar naturally as a context-free grammar and have it parsed. So in this course, we don't focus on LL, LR, LALR. Those are really historical accidents for performance that aren't relevant anymore, in my opinion. We handle LL, we handle LR, we handle LALR. Everything works well in this class. A related question is, in this class, we covered a parsing approach where we kept a chart of parsing states and we memoized things. Some students have wondered, Wes, is that secretly dynamic programming? Now, some of you may not have heard the term dynamic programming before, and it sounds really exciting, like, I don't know, like something out of a television commercial. I'm dynamic and I'm programming. How does that work out? Actually, it's an old term where program means more like table or chart. And the way to think of this is, imagine you're going to a parade or perhaps a symphony or a concert or whatnot, and there's a program written that says, at 1 p.m. we'll do this, and at 2 p.m. we'll play this other song, and at 3 p.m. we'll do that. That's the program for a concert or the program for a schedule of events. And that's the sort of program that we're talking about in dynamic programming. It just means a chart. Dynamic there means that it's updated over time. So dynamic programming is then a special keyword used in computer science to mean I'm going to solve a problem by taking a big chart and writing down answers in it and adding to this chart over time. Dynamic programming is really useful when a problem exhibits what's known as the optimal substructure property. That is, when I can deal with one problem by solving smaller problems and then build the solution back up. Interesting examples of this in the real world are things like spell checkers, protein sequencers, or even trying to figure out the correct order in which to do matrix-matrix multiplication. Comes up a lot, surprisingly. It turns out, yes, although I've been avoiding using the words in class, our memoization approach to parsing really is an instance of dynamic programming. So you've learned your first steps about dynamic programming without it even being a big deal. And then finally in this grab bag, some students have wondered, can we compile an interpreted language or interpret a compiled language? What do those even mean? Well, we've talked quite a bit about interpretation. We interpret HTML web pages and JavaScript on the fly. When we're running our web browser, we read in the input, think about what it means, and spit out the answer immediately. In practice, it's possible to do some of that in advance, to take your source code and build an executable program, some binary code on disk, that you can ship it to someone else, and when they run it later, it will produce the same output, but run really quickly. So in some sense, it's like thinking very hard about the problem, optimizing it once and for all, and then shipping it to all of your friends. Compiling is a lot like packing really well for a trip. You could just make a bunch of trips back and forth, carrying all your clothes, or you could spend a lot of time in your house beforehand, packing a suitcase very carefully, cramming it in there, and then just make one trip. And the question or the trade-off is, well, how far are you going? If you're going across the street, it might actually be faster just to grab things and run back and forth across the street if the program is quick or whatnot. Conversely, if you're going across the country, you probably want to pack things very carefully first because the round trip cost is expensive. Compiled languages are very nice when you know that the program is going to take a while to run, that you're going to ship it to other people. Interpreted languages like Python or JavaScript are really nice when you know it may only be run once or by one person looking at the answer, and that rapid prototyping or rapid development is more important. You want to be able to try things out and have a lot of flexibility. Can you interpret a compiled language or compile an interpreted language? In fact, the distinction is really blurring all the time. Even Python, one of the languages we use in this course, nominally it's interpreted. Right? You run things through a Python interpreter, it gives you the answer. But actually, if you've tried running Python on your home computer, you may have noticed that it often creates a bunch of .pyc files. That's compiled Python bytecode. Your Python interpreter will take a look at your human-readable English text source code, and if it has changed since last time, compile it down into Python bytecode, and then the bytecode can be run quickly later. It's not like packing things into a suitcase. Java actually uses the same approach. Java source programs are compiled down into Java bytecode, which is then interpreted by a Java virtual machine later on. And even a language like C, classical compiled language, we compile it down into some machine code like x86 assembly or x86 machine code, but that's just interpreted by your processor's CPU later on. So in some sense, at the end of the day, everything is interpreted. The question is just how much of this compilation we want to do beforehand. And again, optimization techniques like just-in-time translation or just-in-time compilation, you may have heard this phrase JIT, are starting to blur the lines between these as time goes by. All of the techniques that I'm teaching you, lexing, parsing, looking for errors, optimization, interpreting, environments, all of these are used in both compiled languages and interpreted languages. We'll get to all of those throughout this course, and then you'll be well set to understand either of those two paradigms.